Hello, everyone, and thank you for attending today's webinar, LVAD Physiology and Management, Understanding PI and Other Pump Parameters, with Dr. Jonathan Grinstein from the University of Chicago. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All of the widgets are resizable and movable, so feel free to customize as needed to get the most out of your desktop space. Chrome is the preferred browser for this platform, and refreshing your screen will fix most issues. And with that, I have the distinct honor of welcoming Dr. Jonathan Grinstein as our guest speaker today. Dr. Grinstein is a highly respected cardiologist specializing in the medical management of advanced heart failure. Dr. Grinstein treats patients who require long-term IV medications or continuous infusion pump medications, mechanical circulatory support such as the HeartMate 3 LVAD, and cardiac transplantation. Along with his devotion to excellent clinical care, Dr. Grinstein is passionate about furthering medicine through research. Dr. Grinstein has evaluated and perfected echocardiographic and computed tomography techniques that non-invasively monitor the pressure and volume inside the heart for patients with an implanted LVAD. This technique allows cardiologists to analyze how well a patient is responding to the device and make necessary adjustments in real time. Additionally, Dr. Grinstein is conducting research to develop a smart LVAD that can intuitively adjust its speed based on the physiological needs of the patient. He's using computational fluid dynamics to study and predict blood flow patterns through the LVAD to maximize device performance. So as you can see, there is no one better than Dr. Grinstein to walk us through the wonderful world of LVAD parameters today. Dr. Grinstein, take it away.
Thank you so much, and thank you all for joining us today, and thank you, Abbott, for the platform to speak. We will be taking a deep dive into LVAD physiology with a particular focus in understanding the pump parameters of power, estimated flow, and the often misunderstood pulsatility index. We'll then use this newfound knowledge to improve patient care at the bedside through a variety of clinical scenarios. Here are my disclosures, and here's the agenda for today. So we'll start by briefly describing some of the innovations in the pump design, focusing on the HeartMate 3. This has direct implications on how this pump, compared to other pumps, interpret power to estimate flow to calculate pulsatility index. We'll then focus on the different sources of power that power the left ventricular assist system, and then define pulsatility index and clinical scenarios that influence PI events and pulsatility index. We'll shift our focus onto the determinants of LVAD flow and briefly discuss the difference between true flow and estimated flow. And then we'll put this all together and again walk through some common clinical scenarios and use our newfound knowledge in pump parameters to help improve bedside care. So there's been tremendous improvement in LVAD design over the first commercial success was the HeartMate XVE, which was the pump that was studied in the landmark rematch trial. And although this led to a tremendous improvement in survival compared to optimal medical management, there was significant design flaws or limitations with this technology. Most of this was related to the pulsatile nature of the pump itself. Although pulsatile technology and pulsatile flow is the best to mimic human physiology, it came at a cost, moving parts that were prone to error, mechanical complications and error over time. And so this pump wasn't truly as durable as we wanted or needed it to be for long-term support. So as a whole, the community shifted to a continuous flow technology. The first commercial pump that was successful in this domain was the HeartMate 2. And it again provided excellent hemodynamic support in a continuous flow design, and the design specifically in this pump was an axial design, meaning that the long axis of the rotor is parallel to the direction of flow. But this pump too has some significant design limitations, and the biggest one was that the rotor was suspended by 2 ruby bearings, which led to a lot of heat production, and as we know, heat activates the coagulation cascade and made this pump more prone to thrombotic and cardioembolic phenomena. Our newest technologies attempt to eliminate friction and heat production. The HeartMate 3 on the far right uses a centrifugal design. It is still continuous flow, but the centrifugal nature means that the axis of rotation is perpendicular to the direction of flow. And it uses a full magnetic levitation technology to allow the rotor to sit in the middle of the pump casing with almost no friction whatsoever, and therefore less disruption to the coagulation cascade. The Medtronic Heartwear HVAD uses a combination of magnetic levitation and hydrodynamic levitation, again, reducing friction. So this slide here highlights some of the key design features for the HeartMate 3 that have an objective of reducing activation of the coagulation cascade, reducing shear stress, and improving hemocompatibility. So the first design feature is as mentioned previously, is the fully magnetic levitation technology. This allows the rotor to sit in the middle of the casing with large gaps on all sides, minimizing any point of contact with the housing or the casing of the LVAD itself, and again, minimizing shear stress. This self-centering nature allows for a very large and consistent blood path that, again, reduces blood activation and shear stress as the blood is passing through the rotor. The last design feature, again, with the goal of improving flow and decreasing stagnation, is something called the intrinsic pulsatility, maybe better known as the artificial pulse. And this is when the LVAD rotor slows down and then speeds up rhythmically every 2 seconds to try to improve blood washout. And we'll go into each one of these design features as an individual slide moving forward to provide a little more detail. So here you can see the fully maglev technology with a self-centering rotor. Because of the self-centering nature, we have these large and consistent gaps between the casing and the rotor itself that allows for better blood flow, less activation of the coagulation system. In the middle, you can see these large gaps for the HeartMate 3 with a much smaller gap for a hydrodynamic pump. These gaps can be up to 20 times greater for the HeartMate 3 compared to a hydrodynamic pump. And these improvements aren't just theoretical, they lead to real improvements in shear stress. So for those less familiar with computational fluid dynamics is a study of blood and blood elements as they pass through a confined space. Here you can see shear stress quantified as blood is passing through the inflow cannula and the rotor of the HeartMate 3. Blue and green is good. This means low shear stress, so less activation of platelets, for example, whereas red and orange means high shear stress, which is less favorable. And all of these design features, the self-centering rotor, the large gaps, lead to a low and consistent shear stress and improved flushing and washout of the rotor. This slide here highlights the intrinsic pulsatility, also known as the artificial pulse of the HeartMate 3. Again, we have a set speed that we as clinicians set, but every 2 seconds, the rotor drops 2,000 RPM below the set speed, followed by a 2,000 RPM rise above the set speed, so a delta there of 4,000 RPM. And this cycle repeats itself every 2 seconds to allow for improved washout of the rotor. The HeartMate 3 is actually capable of running in 2 modes when it comes to the artificial pulse. At very low speeds of less than 4,000 RPM, the device actually is set as a constant speed mode, so it's set at the fixed speed. And then another scenario where the constant speed mode will be triggered is if there's a battery or power problem, a low power form setting for the HeartMate 3. In reality, we don't really run the HeartMate 3 at these speeds. The only time clinically we might run at a speed of less than 4,000 RPM would be briefly in the operating room as the device is going in, or in cases of recovery when we're doing a turn-down study or a reverse ramp study. The majority of the clinical operating conditions occur at speeds far above 4,000 RPM, usually above 4,600 RPM. And in this mode, the artificial pulse is obligatorily on. You can see here, again, the speed drops by 2,000 RPM and it quickly rises 4,000 RPM, so 2,000 above the set speed or a delta of 4,000, and it repeats itself every 2 seconds. The last design feature that I want to touch upon is really important for the remainder of this talk because it really defines how the HeartMate 3 compared to the HeartMate 2 interprets power to estimate flow and calculate PI. The onboard computer, the computer that is really the brains of the pump, is in a different location for the HeartMate 3 than it is for the HeartMate 2. For the HeartMate 3, this computer is actually in the pump casing itself. And for the HeartMate 2, the computer is in the controller. And because of this different location, the HeartMate 3 is able to isolate a special type of power called the rotor drive power, whereas the HeartMate 2 uses a composite power for the pump. And this is really the fundamental difference of how these two pumps interpret power to estimate these other parameters. We'll get into this in the next couple slides, but I just want to touch on one additional feature that is unique to the HeartMate 3, and this is the ability to incorporate hematocrit into the flow estimation. So the HeartMate 2 cannot do this. The HeartMate 3 is able to incorporate hematocrit, and as we know, hematocrit is a surrogate for blood viscosity, and so by having a more nuanced appreciation of the blood viscosity, the HeartMate 3 is also able to further enhance its flow estimation. So let's shift focus now to the pump parameters themselves. The first two that we're going to talk about are the LVAD power and the pulsatility index. And when you're looking at the screen or you're doing a device interrogation, these are the parameters on the far right of the screen. As I alluded to in one of the earlier slides, there are many different forms of power that are used to operate the left ventricular assist system. There is the system power, which is a composite term that is used to power both the controller and the LVAD itself. And then in light blue is this pump power, which is also a composite form of power. This includes the power that is used to overcome the resistance of the drive line. It also includes the power that is used to operate the motor. So not necessarily the power to rotate the rotor, but just to operate the mechanics of the motor itself. The amount of energy and power that's needed to push energy through the motor components and the electronics. Another component is something called the bearing power, and this is the power that's needed to overcome the friction or heat losses of the bearings in the HeartMate 2 or to operate the maglev technology in the HeartMate 3. And then finally, all the way at the end in green here is the rotor drive power. And this is the actual power that is used to rotate the rotor and directly attributable to LVAD flow. So one could argue, at least for the clinicians in the audience, that the only power that actually matters is this rotor drive power. Again, this one is directly the power that influences flow. All the other sources of power are obviously important for the engineers in the audience, but less so for the clinicians. The HeartMate 2, as I mentioned, has its computer in the controller itself. And the only power it is able to see is this total pump power, this composite term of total pump power. And when this power is plotted on a power versus flow curve, which you can see here, the relationship for the HeartMate 2 is what you see on the graph here. Is the relationship between power and flow is largely linear under the normal operating conditions. So in flows above 2.5 liters per minute and up to 10 liters per minute, the relationship between power and flow is linear. However, this relationship becomes curvilinear, or said another way, imprecise, at flows of less than 2.5 liters per minute. If the HeartMate 2 is trying to estimate flow based on the power consumption for flows of less than 2.5 liters per minute, it is unable to accurately do so. In fact, it doesn't even attempt to do so. The lowest flow that the HeartMate 2 is going to ever display on the monitor is 2.5 liters per minute because it does not have the ability to recognize or discriminate flows of less than that. The HeartMate 3, on the other hand, because its computer is actually in the pump casing itself, is able to isolate in green this rotor drive power, which, as a reminder, is the power that I said is directly attributable to flow. And when this power is plotted on the power versus flow curve seen on the screen here, you see a very different relationship. The power and flow are still linear in the normal operating conditions, but as you can see, even at low flows of less than 2.5 liters per minute, the relationship remains linear. The relationship becomes curvilinear or imprecise at high flows. But one might argue that this is less clinically relevant. Whether or not a patient is flowing at 8 liters per minute or 10 liters per minute isn't so clinically relevant. They're flowing well, the patient is well supported. What we care more about is when a patient is flowing low flows, because this is when the patient could run into clinical problems. And again, the HeartMate 3 is able to nicely pick up on these low flow states, whereas the HeartMate 2 is not. So to quickly summarize this important feature that I just described, the power that is used for both flow estimation and pulsatility index differs for the two pumps. For the HeartMate 3, with its onboard computer, the power that it is able to recognize is the rotor power, the power that is directly attributable to flow, whereas the HeartMate 2 uses the total pump power, which has less precise flow estimations at low flow states. So what is pulsatility index? Essentially, pulsatility index is the variation of power over time. The exact formula is listed on the slide here, is the maximum power minus the minimum power divided by the average power, and the variable that is plotted on the screen during a device interrogation is a running 15-second average of the pulsatility index. Under the majority of clinical scenarios, you can think of the pulsatility index as a surrogate for underlying heart contractility. Because if a heart is very vigorous, if the left ventricle is pumping well, there's going to be more variations in flow between peak systole and diastole because of the robust nature of the left ventricular contractile force. And since flow and power are linear, as I just showed, that means there's going to be more variation in power during the cardiac cycle, which is the definition of the pulsatility index. Again, as mentioned, PI is variation in power. So PI will be higher the more robust the left ventricle is. The power that is used in the PI calculation, again, is the same power that I just defined in the previous slides. It's the rotor drive power for the HeartMate 3, power for the HeartMate 2. A PI of any time the per second PI differs from that average PI that I just defined, that 15-second running average, by more than 45%. And every time a PI event is triggered, there is an associated speed drop. I'm going to repeat that. Every single PI event has an associated speed drop. And this is something that is less understood by many clinicians. I've heard many times people say when they do a device interrogation that there were pages of PI events, but not associated speed drops, and they think that these are clinically less relevant. That is actually not true. All that's happening in that scenario there is that the periodic log is not picking up the speed drop, but if one were to do a more nuanced or deep dive analysis, for example, a log file, every single PI event would be associated with a speed drop. And in response to a PI event, the speed drops from the speed goes from the set speed to the low speed limit, and then incrementally marches up by 50 RPM until either the set speed is achieved again or another PI event is triggered. Important to point out that only a small minority of PI events are actually due to ventricular suction. The great majority are actually due to relatively clinically benign scenarios. So anything that can cause an abrupt change in preload or afterload has the potential to trigger a PI event. The most common things are just, for example, an abrupt change in preload from a position change. If a patient were to roll onto the right side and maybe transiently occlude the IVC, this could lead to a preload change. Premature beats, PACs, PVCs will also lead to changes in preload. And then abrupt changes in afterload, such as a cough or a sneeze, can also trigger a PI event. A patient is more likely to have a PI event if they're running on the underfilled side of the spectrum. If the LV is underfilled, they're going to be more prone to changes in preload or afterload because in that setting, the LVAD is operating on the flatter part of something called the HQ curve, and therefore changes in pressure lead to more profound changes in flow and more profound changes in power. And if that doesn't make a lot of sense to you now, I promise you it will in just a few slides. So let's do LVAD flow, which is the parameter on the far left if one were to do device interrogation. There really only are three variables that influence LVAD flow. An equation on the top right of the screen defines LVAD flow. So in the numerator, we have the rotational speed of the LVAD, and this one makes a lot of intuitive sense. The faster you rotate the pump, the more flow that the pump is able to generate. And the slower the rotational speed, the less flow. On the denominator is the pressure gradient across the LVAD. So P inflow represents the pressure in the left ventricle. P outflow represents the pressure in the aorta. Anything that brings these two pressures closer together increases flow through the LVAD. And anything that brings these two pressures farther apart decreases flow. So, for example, a drop in preload, such as with a GI bleed, or a rise in afterload, if a patient, for example, didn't take their antihypertensives, would lead to a drop in flow. Conversely, a rise in preload, such as a blood transfusion, or a drop in afterload, such as sepsis physiology, would lead to a rise in LVAD flow. And we can plot the response, the flow response to a pressure gradient in what's called the HQ curve. So here, H on the y-axis stands for the pressure head. This is that same pressure gradient that I just defined, the pressure gradient across the LVAD. And Q is the engineering or electrical term for flow, and this is the flow through the LVAD. So in response to an instantaneous pressure gradient in this example here for HeartMate 3 at a speed of 5,500 RPM, we have a flow approaching 0 liters per minute. And if the pressure gradient were to change to 0 across the LVAD, then the instantaneous flow through the LVAD would correlate to 7.5 liters per minute. There are several HQ curves for a given pump, one for each speed. So here you can see a HeartMate 3 in pink is the HQ curve at a really low speed of 3,000 RPM, and in light blue is the HQ curve for the HeartMate 3 at a fast speed of 9,000 RPM. And the characteristic HQ curves and the set of HQ curves for each speed is really what defines that pump. The HQ curves for the HeartMate 3 are different than they are for the HeartMate 2, which is different from the HVAD, and this really defines how the pump operates. A pump that has a flat HQ curve is going to be more sensitive to changes in preload or afterload. It's going to have more variations in flow if one were to have a variation in preload or afterload, and it's going to better reflect native contractility as a very pulsatile flow pattern. Conversely, a pump that has a steep HQ curve is going to be less pressure sensitive and is going to have a more dampened flow response in response to native contractility. And let's walk through those examples in a little bit, make it a little more clear in the next slide, or actually one additional slide, just to define one additional terminology, something called the shutoff pressure. And this is the pressure gradient at which flow for a given LVAD and a given speed equals 0. Any pressure gradient greater than the shutoff pressure would actually lead to a reversal of flow down the outflow cannula. Okay, so let's go to our examples here. Here is a pump with a flat HQ curve. And if the starting pressure across the LVAD was 90 millimeters of mercury, and then all of a sudden it jumped to 100 millimeters of mercury. So for example, a patient didn't take their blood pressure medications. In this example, the flow would drop from 5 liters per minute all the way down to 0 liters per minute with just a modest change in that pressure gradient. Conversely, a pump with a steep HQ curve, that same pressure change from 90 millimeters of mercury to 100 millimeters of mercury leads to a modest change in flow, only from 5 down to 4 liters per minute, so less pressure sensitive. Here are the actual HQ curves for the HeartMate 2, very steep, less pressure sensitive. Here are the HQ curves for the HVAD, relatively flat, more pressure sensitive. And here's the HeartMate 3. It is bimodal or biphasic. It is flat at low flows and it is steep at high flows. But it's not quite that simple. So what I described before was the instantaneous flow response to the instantaneous pressure. But we know that the pressure gradient is constantly changing throughout the cardiac cycle. So let me walk you through this slide here. So in red, we have the left ventricular pressure versus time tracing. And in blue, we have the aortic pressure versus time tracing. And in this example, you have a patient who's supported by an LVAD, whose aortic valve would not be opening. And I know that because there is a pressure gradient at peak systole. If the valve were to be able to open, the red line would be touching the blue line. And in this case, there is a gradient. There's a connecting the red and the blue line, and this patient's aortic valve would not be able to open. But notice how during diastole, the pressure gradient is quite wide. In this example, maybe around 100 millimeters of mercury. And in peak systole, that pressure gradient is relatively narrow, here around 20 millimeters of mercury. And so the pressure gradient is going to be constantly changing throughout the cardiac cycle, and thus the flow response through the LVAD will also be constant. And this slide here will walk us through that. So if you superimpose the last several slides that I've just presented to you, this is what you get. You get a constantly changing pressure gradient throughout the cardiac cycle. And just to walk you through this, the top line in this insert on the top right is that same aortic pressure. The bottom curve is the left ventricular pressure. And the middle curve is the resultant flow through the LVAD. And you can see that during diastole, we have a pressure gradient here of around 70 millimeters of mercury. And for the blue curve, the HeartMate 2 HQ curve, this correlates to a diastolic flow of around 4 liters per minute. During peak systole, that pressure gradient between the aorta and the left ventricle goes to 0, and the HeartMate 2 resultant flow would be around 10 liters per minute. Let me walk you through this additional video right here. Here's another example of a HeartMate 2 and a HeartMate 3. And as the cardiac cycle progresses, you can see the effects. I'm going to let the cycle play a couple times, and then I'll walk you through it. So again, we have an aortic pressure at the top and a left ventricular pressure at the bottom. And during diastole, gradient is around 100 millimeters per mercury. And so if we focus on the green HQ curve, that correlates to a diastolic flow around 2 liters per minute and a peak systolic flow around 7.5 liters per minute. The exact same pressure gradients, but instead now we substitute a HeartMate 2 for a HeartMate 3, leads to a diastolic flow in blue of around 1 liter per minute and a peak systolic flow of around 10 liters per minute. These changes that we're describing aren't just theoretical changes. This is actually what happens in real patients supported by these different technologies. So this is something called dynamics. When the video plays, you're going to see that the flow is in fact truly pulsatile. So although the LVAD's contribution of flow is continuous, we described in one of our earlier slides that the newest technologies use continuous flow technology, which is true. But the patient's contribution with the constantly changing pressure gradient leads to a net pulsatile flow pattern that you can see in the video. This is a patient on the top left supported by HeartMate 2. On the top right, a patient supported by the HeartMate 3. And on the bottom left, a patient supported by the HVAD. And then in the bottom right, you can see the flow versus time curves, and you can see that the flow is constantly changing throughout the cardiac cycle. There is some flow pulsatility. As I've mentioned several times, power and flow are linear. And so the same conditions and pressure gradients that vary flow will also lead to variations in power. So power will be minimum when there's a large pressure gradient between the aorta and the left ventricle. And power will be maximal when there's a small pressure gradient during peak systole between aorta and the left ventricle. So knowing that this is the relationship, that power and flow are linear, it is much easier, at least for the heart failure doctors in the audience who are used to thinking through flow and less used to thinking through power, to conceptualize pulsatility index as a variation in flow. Because anything that causes a large variation in flow will also power, given the one-to-one linear relationship, and thus this would be interpreted by a device as a high pulsatility index, since PI by definition is a high variation in power. So let's walk through this theoretical clinical scenario. Here we have something that abruptly causes a drop in diastolic flow, for example, maybe a balloon pump that was inflating, and then an abrupt rise in systolic flow, for example, a balloon pump deflating. This scenario here would lead to a large variation in flow, which, given the one-to-one relationship between flow and power, would lead to a large variation in power, which would be interpreted as the device as a high pulsatility index. And as one final reminder before we really get into the clinical scenarios, I'm going to again remind you that the power that is used to estimate flow and to calculate pulsatility index differs between the HeartMate 2 and the HeartMate 3. With the computer in the HeartMate 2 being in the controller itself, it uses total pump power, which is imprecise at the low flow range. The HeartMate 3 has its onboard computer in the pump case in itself. It uses the rotor power, and it is imprecise at high flows, but it is very precise at low flows. So, putting everything together, this is how the HeartMate 2 and the HeartMate 3 interpret power, estimate flow, and the different regions of the spectrum. So let's focus on the dotted line, which is the HeartMate 2. And you can see that the HeartMate 2 is able to nicely pick up high flows. You see a nice curvilinear aspect of the flow estimation, even at high flows. But when we get to the low flow states, the HeartMate 2 is unable to estimate flows of less than 2.5 liters per minute, and you see that flat line at that level of 2.5 liters per minute. Although actual flow is in fact lower in this scenario here, the HeartMate 2 does not know that. It will ever tell you the flow is on its parameter is 2.5 liters per minute. In the solid blue line, you can see the HeartMate 3 is imprecise at high flows. It cuts off and has a flat line at the high flow state. But it is very precise at estimating flows of less than 2.5 liters per minute. And in this example, is able to pick up all of these low flow events. So just to quickly summarize, the HeartMate 2 is going to underestimate low flows. The HeartMate 3 is going to nicely pick up on low flow events. And again, this is related to power versus flow relationships of the HeartMate 3 versus the HeartMate 2. Okay, let's put it all together and let's clinical scenarios and use these parameters to manage our patients. So what happens when there's a change in volumes? During ventricular filling, for example, a hypervolemic state, we have a rise in left ventricular pressure. And when that happens, left ventricular pressure gets closer to aortic pressure. Since that pressure gradient is now narrowing, and I've described that that's a scenario that increases flow through the LVAD, mean LVAD flow is going to go up. However, systolic flow is going to be augmented more than diastolic. And this has to do with the Frank-Starling mechanism and the response to volume loading and cardiac output. And if that doesn't make a lot of sense to you, I'm hoping the next slide, when we focus on the pressure volume loops, will explain why systolic flow is augmented more than diastolic. But for now, just take it that with a volume challenge, mean flow goes up, systolic flow goes up, and diastolic flow goes up, but systolic flow goes up more than diastolic flow, and pulsatility or flow pulsatility widens. During hypovolemia, the opposite occurs. The left ventricular pressure drops, the pressure gradient across the LVAD widens, peak flow, mean flow, and diastolic flow go down, systolic flow drops more than diastolic flow, and pulsatility narrows. But let me walk you through why pulsatility changes as much as it does with a volume load. So for those less familiar with a pressure volume loop, let me walk you through it. The bottom curve that is here represented as EV/PVR is the end diastolic pressure volume relationship, and this defines the diastolic properties of the heart. The straight line at the top, designated as ES/PVR, is the end systolic pressure volume relationship, and this defines the systolic properties of the heart. The slope of the end systolic pressure volume relationship is the contractility of the left ventricle. Now let's shift our focus to the middle red curve. That bottom right inflection point is end diastole, and it represents the diastolic pressure and volume at end diastole. When systole occurs, there's an abrupt rise in pressure as the left ventricle begins to contract. Notice how in a patient supported by an LVAD, there is no such thing as an isovolumetric phase. In a non-LVAD supported patient, there would be a straight vertical line during isovolumetric contraction. However, in a patient supported by an LVAD, there is continuous unloading of the left ventricle because of the LVAD itself, and the curve is shifted diagonally to the left. Then the heart relaxes and we have a drop in left ventricular pressure, but again, we have constant unloading, so we still have a diagonal downslope. And at the very bottom of the curve, diastole occurs again, and we have filling of the left ventricle. Now let's focus on what happens when we have a volume challenge. So on the blue curve is a hypovolemic state, and the purple curve is a hypervolemic state. And notice how the diastolic pressure rises, but only modestly so, as the curves shift up the end diastolic pressure-volume relationship. But the systolic pressure augments significantly more than diastolic pressure. And so, since diastolic pressure is going up, the gradient between the aorta and the left ventricle will narrow, and diastolic flow will increase. But the gradient during systole between aorta and left ventricle will narrow far greater, and systolic flow will be augmented more than diastolic flow, and flow pulsatility will increase with the volume challenge. Let's take a look at these clinical scenarios using the HQ curve. So here we can call this state hypervolemia, or we can call it normal volemia, for example. We'll contrast this to a hypovolemic state in a second. And this is going to represent our representative example. So I'm going to spend a little time focusing on this one here, because we're going to keep going back to this this HQ curve when we describe the different clinical scenarios. So here, again, in the insert, in red, we have aortic pressure. In blue, we have left ventricular pressure. And then purple, we have LVAD flow. During diastole, we have a pressure gradient of 80 millimeters of mercury, which on this HQ curve correlates with a diastolic flow of 4 liters per minute. During peak systole, the red line and the blue line are touching. The gradient is 0, and the peak systolic flow is 7.5 liters per minute. Now, when we make somebody hypovolemic, notice several things. First of all, if you look at the insert, there is now a gap between the aortic pressure in red and the left ventricular pressure in blue. The systolic pressure gradient, which was previously 0, is now around 25 or 30 millimeters of mercury, and the diastolic gradient is still around 80 millimeters of mercury. And so here we have an example. Mean flow, which would be the center of this arrow on the far left or the HQ curve, systolic flow and diastolic flow have all changed. But in this case, in this example, systolic flow was a decrease more than mean flow and diastolic flow. Pulsatility will narrow. Let's take a look at the same scenario with what's called the flow versus time curve. So at the start of this flow versus time curve, we have a normal volemic state, and then an insult occurs, maybe a GI bleed. And you can see here that systolic flow drops and diastolic flow drops. But the overall variation in flow at the far end of this flow versus time curve is actually greater than the starting condition. The difference between peak flow and minimum flow is greater. Said another way, there is an increased variation in flow. As I've mentioned on numerous occasions, flow and power are linear. So the enhanced variation in flow would be interpreted by the HeartMate 3 as an enhanced variation in power, which is the definition of a pulsatility index. PI is variation in power. So in this scenario, a HeartMate 3 would recognize a hypovolemic insult as an increase in PI. Conversely, the HeartMate 2, as I've mentioned, is not good at predicting or estimating flows that are less than 2.5 liters per minute. So although actual flow in this scenario is low and way less than 2.5 liters per minute, the HeartMate 2 does not see this. It only sees the flows up to 2.5 liters per minute. And so the variation in flow that the HeartMate 2 sees is much less. Variation in flow is linear and proportional to variation in power. And so the HeartMate 2 is going to see this scenario as a drop in a variation in power, and therefore a drop in PI. And PI decreases in response to hypovolemia as interpreted by the HeartMate 2. Okay, let's now shift focus to the effects of blood pressure. With hypertension, the aortic pressure obviously goes up. That is the definition of hypertension. And so the pressure gradient between the aorta and the left ventricle will widen with hypertension, and flow will decrease. However, diastolic flow will drop more than systolic flow, and flow pulsatility will widen. And this will become clear on the next slide. Just very briefly, the reason diastolic flow is influenced more than systolic flow is because during diastole, we are operating on the flat part of the HQ curve, And as I've mentioned previously, and as I'll show you on the next slide, when that occurs, we are more sensitive to pressure changes. More pressure changes lead to a more profound drop in flow when you're on a flat part of the curve. The opposite occurs during hypotension. With hypotension, aortic pressure drops, the pressure gradient across the LVAD narrows, and flow increases. But again, diastolic flow will be influenced more than systolic flow, and pulsatility will narrow. So back to our representative example, we'll call this the normotensive state. During diastole, we have a pressure gradient of 80 millimeters of mercury. This leads to a diastolic flow of 4 liters per minute. During peak systole, we have a gradient of 0 millimeters of mercury, which leads to a peak systolic flow of 7.5 liters per minute. And now we make our patient hypertensive. So again, on the insert, let me draw your attention there. Notice how we have a larger gap between aortic pressure and left ventricular pressure because the patient is now hypertensive. Yes, diastolic gradient has increased. It went from previously 80 to now 100 millimeters per mercury. But notice what happened to our systolic pressure. Our systolic pressure was previously, the gradient was previously 0, and now it is 20 millimeters per mercury. So what does that do to our net flow when you look at the HQ curve? Our diastolic flow, which was previously 4 liters per minute, is now down to 1.5 liters per minute. And our systolic flow, which was previously 7.5 liters per minute, is now down to 7 liters per minute. So yes, peak systolic flow has dropped, and yes, mean flow has dropped, but diastolic flow has dropped far greater than systolic flow, and flow pulsatility widens. And again, this is because during diastole, we are operating on the flatter part of the HQ curve, and we are more pressure sensitive. Back to our flow versus time curves, and here we'll focus on HeartMate 3. In response to hypertension, both systolic flow goes down and diastolic flow goes down. Again, diastolic flow goes down more than systolic flow. Because of this, there is more variation in flow, which means there's more variation in power. The HeartMate 3 sees all of this variation in flow and power and correctly interprets this as an increase in pulsatility index. The HeartMate 2, on the other hand, has imprecision of flow estimations at low flows. It does not see all this variation in flow, and thus it does not see all this variation in power. And thus, in this scenario, the pulsatility index actually decreases compared to the baseline condition. Okay, the next clinical scenario that we're going to talk about is RV failure. RV failure, at least when it comes to the left ventricle and the LVAD, is pretty much the same as a hypovolemic state. The mechanism is obviously different. Here, the LV is underfilled because the RV is having difficulty delivering blood to the left ventricle, but the result is still going to be the same. Left ventricular pressure is going to drop because of an underfilled left ventricle. The pressure gradient across the LVAD is going to widen and flow is going to decrease. The difference here, however, is that in response to an inotrope, for example, we can restore normal flow and normal pulsatility. And why is that? Well, let's look at the pressure volume loops. And I want to point out here that although we are talking about RV failure, this is still a left ventricular pressure volume loop. And so in a struggling right ventricle in blue, we have an underfilled left ventricle. So the curve starts lower down on the volume curve because the left ventricle is underfilled. And we have a relatively flat end systolic pressure volume relationship because the heart, both ventricles are. We now add an inotrope, and this is the red curve. And we have improved filling of our left ventricle because the right ventricle is now more robust. It's now pumping more vigorously. And so the red curve marches up the end diastolic pressure volume relationship. We have a higher starting volume point at the end of diastole. And notice how the red line now is able to eject all the way to this more steep end systolic pressure volume relationship, the dotted end systolic pressure volume relationship, because inotropes improve RV contractility, but also LV contractility. So the net result here, if you look on the far right of the figure, is that diastolic pressure did increase modestly, but systolic, or at least peak systolic pressure, increased far greater. And again, both diastolic flow will go up because of this rise in diastolic pressure, but systolic flow will increase more than diastolic flow, and flow pulsatility will widen. The next clinical scenario we're going to discuss is aortic insufficiency. So with aortic insufficiency, there's some interesting physiology occurring. In the aorta, let's focus on the aorta first. We have antegrade flow down the aorta, so the normal path of flow in any patient, whether they have an LVAD or not, but we also have retrograde flow back across the aortic valve. So the aortic pressure dissipates very quickly. There's runoff in both directions, and aortic pressure drops very quickly. At the exact same time, because of the regurgitant volume going back into the left ventricle, the LV pressure is actually going to rise. So we have a scenario where the aortic pressure is going to drop, LV pressure is going to rise, the gradients become closer together, or so the pressure become closer together, so the gradient narrows, and LVAD flow will go up with aortic insufficiency. Diastolic flow will be augmented more than systolic flow, which will become clear on the next slide, and pulsatility narrows. So why does diastolic flow get influenced more? So this is a paper that we published on AI a few years ago, but it has a good example, a good representation of what happened to diastolic and systolic flow. So let's focus on systole. In systole, we have, because of the enhanced loading of the left ventricle, because of the AI itself, we have a slightly improvement of peak systolic flow during systole. The blue line here represents a very severe case of AI, the red line a less severe case of AI. But notice how the systolic flow goes up as AI severity goes up, but only modestly. Now let's focus on the bottom to fix diastole. With diastole, we have, again, antegrade flow down the aorta, but also retrograde flow back into the left ventricle. So the afterload, or aortic pressure, dissipates very quickly. You can see that the blue line has a more pronounced drop in afterload, which then translates into a more abrupt rise in diastolic LVAD flow compared to the red curve. So the more severe the AI, the more abrupt rise in diastolic flow. And you can see that the two arrows on the far right, the height of the column comparing peak systolic flow to end diastolic flow, narrows as AI severity worsens. So said another way, the flow pulsatility, or the difference between peak systolic flow and diastolic flow, goes down as AI severity increases. Back to our representative example, again, the same clinical scenario in somebody without aortic insufficiency. A diastolic pressure gradient of 80 millimeters of mercury leads to a diastolic flow of 4 liters per minute. A peak systolic gradient of 0 leads to a peak systolic flow of 7.5 liters per minute. And now we introduce aortic insufficiency, and what happens? Well, I'm going to first point out to you that because of the AI, if you look at the insert, the diastolic pressure gradient has narrowed. It previously was 80, and now it is 60 millimeters per mercury. And that's because of both a drop in aortic pressure, but also a simultaneous rise in left ventricular pressure. Peak systolic gradient, though, is still 0. So the peak flow is still 7.5 liters per minute, but the diastolic flow, which was previously 4 liters per minute, is now 5.5 liters per minute. So we have, in this example, the same systolic flow, a rise in mean flow, and a very pronounced rise in diastolic flow, and so flow pulsatility narrows. When we look at the flow versus time curves, again, you can see a relatively unchanged systolic flow, an abrupt increase in diastolic flow. The HeartMate 3 sees this as a reduction in variation in flow, which means there's a reduction in the variation in power, which is what the definition of pulsatility index is, and so the PI decreases with the HeartMate 3. The HeartMate 2, it sees all this just fine, because again, its problem is low flows, but AI is a problem with high flows. So the HeartMate 2 interprets AI the exact same way: reduction in variation in flow, a reduction in variation in power, and thus a decrease in PI. Okay, what happens when the left ventricular contractility changes? Let's start with a decrease in LV contractility. So when the LV is contracting less, the diastolic pressure will increase. We have less pronounced unloading of the left ventricle, so LV diastolic pressure goes up. And this will have a tendency to increase diastolic flow. At the exact same time, LV peak systolic pressure will be less because the LV is less robust. It's not able to generate as much contractile force. And so the pressure gradient during peak systole will be wider, and systolic flow will go down, and mean flow will also go down for that matter. So with a decrease in contractility, we have a drop in systolic flow and a rise in diastolic flow, and flow pulsatility narrows. The opposite occurs with an increase in contractility, such as a patient who is showing signs of recovery. When the LV is recovering, the diastolic pressure is going to be lower because the LV is more vigorously contracting and it's able to self-vent, it's able to self-unload the left ventricle. So the diastolic gradient will be greater and diastolic flow will go down. The LV peak systolic pressure will be higher because of an increased contractile elements, and the systolic pressures will be closer to aortic pressure, and so systolic flow will go up. So we have a scenario here where systolic flow goes up, diastolic flow goes up. The difference, the flow pulsatility widens. Here's another example of that using the pressure volume loops. In blue, a low contractile state, in purple, a high contractile state. You can see that as the contractility increases, diastolic pressure actually goes down because of better unloading of the left ventricle. So diastolic flow will go down. But with enhanced contractility, we now operate on a steeper end systolic pressure volume relationship, and systolic pressure goes up, and thus the gradient between the LV and the aorta narrows, and peak systolic flow increases. And pulsatility obviously will increase as the contractile forces increase. All right, so when, again, we focus on the flow versus time curve, we see a rise in systolic flow, a drop in diastolic flow. The HeartMate 3 sees all this as an enhanced variation in flow, which is linear to power, and so therefore there's an enhanced variation in power, and the HeartMate 3 sees this as an increase in pulsatility index. The HeartMate 2, although it loses some of the flow discrimination at low flows, overall still sees this scenario as an increase in flow. Maybe slightly less than the HeartMate 3 would have in the same clinical scenario, but if you look at the variation in flow on the right side of this curve compared to the initial starting point, there still is more variation in flow, and therefore there is still more variation in power, and the HeartMate 2 still will see this as an increase in pulsatility index. The last parameter that we've kind of glanced over until now is the RPM, which is in the middle of a device interrogation on the screen that you can see here. So what happens when you change the RPM to all these different parameters? Well, it's not as easy or straightforward as you might think at first glance. So at first glance, you say, okay, I've already told you that if you increase the RPM, you're going to increase flow. And if you decrease RPM, you're going to decrease flow, which is true. If you focus on just the RPMs themselves, that is true. But the pressure gradient is also going to change as the RPMs are changing. So for example, if I were to decrease the rotational speed of the pump, I'm going to have less unloading of my left ventricle. And because of that, my left ventricular pressure is going to be higher, which in and of itself, if I ignore the RPM element to it, if I just raise LV pressure, that would have a tendency to increase flow. But we can't just ignore the RPM. I've decreased my RPM in this scenario here. So what wins out? Does the drop in pressure gradient win out, or does the drop in RPM win out? And the answer is RPM wins out. And the reason for this is we are now operating on a different HQ curve, and flow will drop and pulsatility will widen as we decrease RPMs. And this will make a little more sense on the next slide. But let me just quickly walk you through the increased RPM scenario. With an increase in RPM, although the diastolic gradient will widen, RPMs win out, flow increases, and pulsatility will narrow. The next slide will hopefully make this a little more clear for you. So we'll go back to our representative example. Here you can see, we'll call the representative example our high RPM state. We have a diastolic gradient of 80 millimeters per mercury and a diastolic flow of 4 liters per minute. a peak systolic gradient of 0 millimeters per mercury, which leads to a peak systolic flow of 7.5 liters per minute. We now drop the RPMs. And notice how the pressure gradient has narrowed. LV pressure has increased, and the gradient went from previously 80 to now down to 70 millimeters per mercury. The peak systolic gradient is still 0, but we are now operating on the blue HQ curve. We're no longer on the green HQ curve, we're on the blue one because we've dropped our speed. And so that pressure gradient of 70 correlates to a diastolic flow of 0. That pressure gradient during peak systole of 0 correlates to a peak systolic flow of almost 6 liters per minute. Systolic flow goes down, mean flow goes down, and diastolic flow goes down far greater, and flow pulsatility widens. All right, the very last clinical scenario that we're going to touch upon are abrupt changes in either preload or afterload. So let's focus on afterload first, and a good example of that is the intra-aortic balloon pump. With an intra-aortic balloon pump inflation, the aortic pressure will increase, which will increase the pressure gradient across the LVAD, and flow will go down. During a balloon pump deflation, aortic pressure will drop, the flow across the LVAD will augment. And here you can see on the figure on the right, a balloon pump in 1 to 3 mode, and you can see that there is a variation in both diastolic and systolic flow because of that. On the bottom figure, you can see the effects of an abrupt change in preload. For example, with a premature ventricular beat or a premature atrial contraction, after the premature beat, there is a compensatory pause, and therefore the LV is going to fill more. The rise in left ventricular pressure leads to a narrowing of the pressure gradient across the LVAD, and flow will be augmented in the beat after the premature beat. Back to our flow versus time curve, let's focus on the balloon pump. You can see that when the balloon pump inflates, diastolic flow goes down, and when the balloon pump deflates, systolic flow goes up. This is interpreted by the HeartMate 3 as an increased variation in flow, which translates to an increased variation in power and thus an increase in pulsatility index. The HeartMate 2 loses some of this variation in flow because of its imprecision at low flows. But overall, there still is an increase in flow variation compared to the starting condition, and thus an increase in variation in power, and it still does interpret this as an increase in pulsatility index. All right, so we are nearing the end here. The last 3 slides are summary slides, and I'm not going to go over all of the details. This is mostly for your reference, but this figure here talks about all the different clinical scenarios we talked about, and it plots them in a curve that on the y-axis is the pulsatility index. So the high up on the y-axis is a high PI, low on the y-axis is a low PI, and on the x-axis is the estimated flow. Far on the right, high estimated flow, and far on the left is a low estimated flow. So at one extreme, we have aortic insufficiency, which has high estimated flows and a low pulsatility index. And at the other extreme, we have hypertension, which has a low estimated flow with a wide pulsatility index. I personally like these next 2 summary slides a little better, and let me walk you through them. I'm not going to go through each individual line because this is really what we talked about for the whole talk. But I will walk you through some important similarities and differences between the HeartMate 3 and the HeartMate 2. So let me first point out that the normal operating conditions, the normal range for flow, PI, and power are the same for the 2 pumps. Normal flow is between 3 and 6 liters per minute, PI between 2 and 6, and power between 3 and 6 watts. And this is the same for the HeartMate 3 as it is for the HeartMate 2. Another important observation is that estimated flow and power always go in the same direction. We have a downward trajectory for the estimated flow, a downward power, an elevation estimated flow for AI, and elevation estimated power for the AI as well. And again, for a balloon pump, we have a drop in estimated flow and a drop in estimated power. This is the same. They always trend in the same direction for the HeartMate 2 and the HeartMate 3. That is estimated flow and power. They always go in the same direction. But true flow might, under certain circumstances, be different from estimated flow. And the classic example of that is a rotor thrombus. In a rotor thrombus, the power that the system is using to generate rotational speed is not related to true flow. It is an exogenous event. The power is being artificially going up because the rotor is actually having difficulty overcoming the drag of the thrombus itself. So we have a certain set speed, and the device is trying to achieve this set speed, but it can't, or is having difficulty doing so because of the resistance and drag of the thrombus itself. So power is going to go up to overcome this resistance. And since estimated flow is based off of the power, the estimated flow is also going to appear like it's going up on the device interrogation. But in reality, true flow is going down here because of the actual thrombus and obstruction of flow itself. The very last thing I'm going to point out is really what we've been focused on for the entire talk, is the difference in the pulsatility index between the HeartMate 3 and the HeartMate 2. In clinical scenarios that lead to underfilling of the left ventricle, the HeartMate 3 is able to nicely see this variation of flow and recognize it as a variation in power and picks up on this as an elevation in pulsatility index. These same clinical scenarios, hypovolemia, hypertension, tamponade, are not fully appreciated by the HeartMate 2. It does not have good low flow discrimination, and it interprets these as a reduction in variation in flow and thus a reduction in variation in power and a low pulsatility index. I want to thank everybody for tuning in today. I know this is a very complex topic, and if I'm being honest with you, it took me several times to go through this until I really felt comfortable with it. And so if you have any questions whatsoever, please reach out to me either by email or Twitter. I'm happy to walk you through things, and I even provide some more examples to really hone this in and really make sure we're all experts on these parameters. Thank you all for your time.
Wonderful. Thank you so much, Dr. Grinstein, for that fantastic presentation. You know, in less than an hour, you have so eloquently explained how our modern-day MCS devices interface with the patient's clinical condition. And I'm confident that everyone listening today will walk away with more knowledge to help in the management of their MCS patients. On behalf of Abbott, I'd like to thank our audience for tuning in today. Please follow us on Abbott Cardio on Twitter for more upcoming educational opportunities. Thank you all for all that you do for your patients and communities. We hope to see you next time. Thank you.